Well, hello and welcome to Monday Night Calculus. My name is Curtis Brown, and I've got Steve Kokoska and Tom Dick here with me. Really excited to have these guys here sharing their knowledge. We are diving into those important existence theorems. You guys know them as IVT, EVT, MVT. So we'll be playing around in that space of existence, which is great. If you are hanging around and you'd like to have those problem sets, the problem sets that they're going to look at tonight are down in the description. I'll post a link in the chat box as well, just in case. But if you expand that description for tonight's video, you can jump in and see that. And if you stick around, teachers, to the very end, I've got my email address. I'll post it in the chat box at the very end. You can email me and get some professional development hours along with Steve Kokoska's got his book there advertised in the back shot of his video. So as he's chatting tonight, I'll post a little link for you guys to get a little more information about that as well. So Steve, I think I can turn it over to you. I caveat have not done my homework.
Oh no.
So we'll have to rely on the chat tonight
Okay,
if
that's a
there's any
deal.
questions.
That's a deal as long as you're monitoring that. Thanks, Curtis. Thanks for being our MC once again. Great to be with you and Tom. We've got some great problems again this evening. We are going to talk about the IVT, the EVT, and the MVT. These are, with a caveat here, Tom, don't let me make a mistake on this one. These are three abbreviations that in general students can use on the AP Calculus exam, and readers will know what they mean. So if they write MVT, we know they're referring to the mean value theorem. There are others, of course, that they may use, but we don't know exactly what they mean. But these three we generally accept. I know there's a lot of conversation now in the AP pre-calculus community about whether or not students can use that abbreviation AROC for average rate of change. I think that's still debatable, but I guess most teachers recognize that abbreviation too. But indeed, Curtis, we're going to talk about these existence theorems. And the first problem relies upon the graph of this piecewise linear function. And the graph of f is shown in this figure. It's made up of three straight lines. You'll notice that it has domain down here, -4 to 4. It's open on the -4 end. It's closed on the 4 end. It's open on the -4 end. You'll notice it has an open circle here, if you can see that graph. And it's got a closed or a dot over here where x is equal to +4. So it's closed over there on that end. So before we get to examining these theorems and how they might apply to this function, let's first think about completing this table of values. And this table has some x values from -4 up to 4 by ones. And we're asked to complete this table and find values of f of x and f prime of x. Now, it does say in the instructions here to use DNE for does not exist if a value doesn't exist, but I wanted to add a little bit here. You know, sometimes there's a subtle difference, a subtlety between undefined and does not exist. In calculus, we often use does not exist when we're examining things like the first derivative, when we're examining limits, when we're examining the second derivative, when we might say, well, the second derivative doesn't exist at x equals 5. But UND or undefined is often reserved or often used when we just simply take a look at a function and ask, does the value of the function exist at, say, -4 or at 4 or at 18? Now, I put DNE in all of these places where I couldn't get a value. But I understand that at least in this place right here that I've circled, I might instead put undefined. So that's a subtle difference between those two terms, undefined and does not exist. And the reason that I bring that up is because of the difference between maybe pre-calculus and calculus. In the AP pre-calculus course, we would probably use undefined more freely or more commonly because we're not taking a look at limits. We're not taking a look at the first derivative or the second derivative. But in a calculus class, we probably use DNE more often, associated with limits and the first derivative and the second derivative. So all that is aside, let's see if I can fill out this table. For x equal to 4, the function is not defined, so certainly the first derivative is not defined. For x equal to -3, I simply went up to the table and read off the value of f, from the graph. And for the first derivative, well, let's see. Fortunately, between 0 and -4, between -4 and 0, open on the -4, and the graph is simply a straight line. I don't have a formula for this function f, but I do know that this straight line has a slope, and I know that's the derivative. And I think the slope of that line is -1. So in fact, that's the value of f prime at those three values of x, -3, -2, and -1. When we get to x equals 0, the value of the function is 0. Kind of hard to see there, but it does go through the origin. And the value of the first derivative does not exist. Why? Because there's a sharp edge or a corner there. Again, I don't have a formula for f. I'm not going back to the definition of the derivative, but I know that if I have a sharp corner there, the derivative doesn't exist. And I think this was something that Tom showed us a couple of webinars ago. If we try to zoom in over and over again near 0, we cannot make the graph of f straighten out and look like a straight line. It's got that sharp edge or corner, which in some sense we can't get rid of. We can't make it look locally linear. The derivative does not exist. At 1, the value of the function is 0. At 1, the value of the derivative is 0. Why? Because, well, I'm on a portion of the graph of f that is a straight line with slope 0. At 2, the value of the function is 1. Be careful, there's an open circle right there and a solid dot there. So the value of the function at 2 is 1. The derivative doesn't exist. Heck, if the derivative exists, the function has to be continuous, and it isn't. So we know the derivative doesn't exist there. At 3, the value of the function is 5/2. The value of the derivative is 3/2. Once again, the function is a straight line in that interval from 2 to 4. So I simply find the slope, and I think it's 3/2. And let's see, the value of the function at 4 is 4, and the derivative does not exist at 4. Well, because we need to take a look or consider the definition of the derivative, and we can't come in from the right-hand side. We don't have a limit coming in as x approaches 4 from the right. The derivative doesn't exist there. Now, some of you are thinking about a left-hand and a right-hand derivative. You're correct. Well, we didn't ask that here. We're asking for what I might call an overall derivative. So I think those are okay. I think those are the values in that table. If I were to redo this one, I think I'd plug in a UND over there, but leave everything else the same. Fantastic. Okay, I'm going to answer these questions on the problem set that we posted. But I'm going to do these in a little bit different order, a little bit more maybe logical order in my weird way of thinking about things. There were 4 intervals at question here that we wanted to look at. -4 to 4, -3 to 0, -1 to 2, and 2 to 4. And we wanted to examine, excuse me, the intermediate value theorem, the extreme value theorem, and the mean value theorem on those 4 intervals. And before I do that, I thought it would be good to just recall those theorems and what the assumptions are, what the conclusions are. I won't read through all of these, but I will make a note that at least part of the assumptions in all of these is that the function must be continuous on the closed interval. You will remember these conclusions about the intermediate value theorem, finding an intermediate value theorem, the EVT, that there are extreme values, and the MVT is that there is a value so that the derivative is equal to the slope of that secant line at some point C. I reminded that these are existence theorems. I remember when I was first learning these, I remember my calculus teacher in college saying they're existence theorems, but they're kind of sneaky because they tell you that there are these numbers C and D in some instances, but they don't tell you how to find them. You have to find them in some sneaky way or tricky way or problem-solving way. Okay, so here's how I'm going to attack these. Here's the first interval. I'm going to look at these bi-intervals. The interval is -4 to 4 closed. Well, the first thing I notice is that the function is not continuous on that closed interval. In fact, it's not even defined at -4. So this is an easy one. I can't answer, or the IVT, the EVT, and the MVT do not apply on this closed interval because the function f is not continuous on that closed interval. Now look, there may be an intermediate value, there may be extreme values. The mean value theorem may hold. I don't know that yet, but we're not guaranteed any of that because the assumptions for these theorems are not met. So I'm done with that one. That one's easy. Thanks, Tom, for that. The next interval is -3 to 0. Well, I'll take a look at these three theorems separately. For the intermediate value theorem, the function is certainly continuous on that closed interval -3 to 0. So f of -3 is 3, f of 0 is equal to 0, and we were asked to find a value of c so that f of c is equal to 3/2. Can we do that? Sure, because 3/2 is in between 3 and 0. So there must be a value in between -3 and 0 so that when we evaluate the function at that input value, we get 3/2. Now, I don't have a symbolic or an analytic expression for f. So the way that I attacked this was by simply looking at the graph. And I realized, well, let's see, where's 3/2? It's about here. Yep, and in fact, if I evaluate the function at -1.5, I get 3/2. I feel pretty good about that one. Well, what about the EVT, the extreme value theorem? Once again, the function f is continuous on this closed interval -3 to 0. So the EVT tells us there must be an absolute maximum value on that interval. There must be an absolute minimum value. How do I get it? Well, in this case, once again, I'm just going to simply look at the graph. I'm going to color a little bit on my graph. I'm looking at -3 to 0, that closed interval. Let's see, -3 to 0. So I can see pretty easily that the absolute maximum value is 3, the absolute minimum value is 0. And yes, I'm making use of a little bit of that straight line. I know about that line. I know its slope. I know the points that it goes through. And that's how I found the absolute max and min. And finally, the mean value theorem down at the bottom here. F is continuous. Two assumptions I need to think about here. Is F continuous on the closed interval -3 to 0? Yes. Is it differentiable on the open interval -3 to 0? Yes, it is. So I'm going to find that difference quotient, f of 0 minus f of -3 over 0 minus a -3. I think when I plugged everything in, when I looked at the values from the graph, I got a -1. And so that says there must be a value of c in the open interval -3 to 0, so that f prime of c is equal to -1. And indeed, there are many here because that straight line has a slope of -1, and I just picked -2. So pretty straightforward, nice applications of those three theorems to this particular piecewise defined function. I like that one. Well, how about this one? The interval -1 to 2. This one is pretty straightforward and easy also, I think. F isn't continuous on that closed interval -1 to 2. I'm done. The assumptions for these three theorems are not met. I don't have to worry about this one at all. So I'm done with that one. And 4 is interesting. This is the interval 2 to 4. Let's take a look at this one. For the intermediate value theorem, is f continuous on that closed interval? You bet it is. F of 2 is 1, f of 4 is 4. And we were asked, is there a value of c such that f of c is equal to 5/2? Well, let's see. 5/2 is in this interval, 1 to 4. So yeah, there's got to be a value. How did I find it? Well, I took a look at the graph and I thought a little bit about that straight line segment and what the slope is. And indeed, f of 3 is equal to 5/2. That is a value of c that satisfies the conclusion of the intermediate value theorem. Pretty cool. The extreme value theorem, f is continuous on the closed interval 2 to 4. There's got to be an absolute max. There's got to be an absolute min. Again, by looking at the graph, there's an absolute minimum value of 1. There's an absolute maximum value of 4. And the mean value theorem, well, let's see. F is continuous on 2 to 4 closed. It's differentiable on 2 to 4 closed. I'll take a look at that difference quotient. Let's see. F of 4 minus f of 2, did I do that right? Is 3/2. So it turns out that C can be any value between 2 and 4 because there's a straight line between 2 and 4 for f. So in fact, f prime of 3 is equal to 3/2. That is a value of C that satisfies the conclusion of the mean value theorem. Pretty cool. Now, there was one more part to this problem number 1. It was a true-false question. It says, look, the function f attains its absolute minimum on its domain at a value of c, where f of c is equal to 0, and f prime of c is equal to 0. Let's see, is that true? Well, it turns out to be true, and I'm going to sneak a peek back up here for a minute. Let's see if I can. Yeah, it turns out, just by looking at that graph, that the absolute minimum value of that function is indeed 0. And it attains that absolute minimum value at any value in between here, between 0 and 2, but I'm going to pick that value 1. And the reason is because f of 1 is 0, and the derivative of that function at 1 is also 0. And so I think that makes this statement true. A little tricky because you might think about picking x equals 0, but I think that's true. Cool. Any questions at all, Curtis, that have come in?
Nope, nothing so far.
All right, Tom, a little bit of technology?
Sure, Steve. There was one point I wanted to make before
Oh.
you left your thing there.
Sorry, go ahead. Go ahead.
It's just a little bit of a subtlety having to do with the language we use around theorems. And I wanted to look at your that interval from -1 to 2.
Okay.
Closed interval. And as you pointed out, I mean, none of these theorems apply on that interval because the function's not continuous on that closed interval. So we would say, in particular, the mean value theorem does not apply. I think sometimes the language, students will mix up the language a little bit and say, well, but the mean value theorem is true on that interval.
It is indeed.
Well, the theorem's not true. It cannot be applied, but there is a value. The conclusion of the mean value theorem happens to be hold on this interval. That's the subtlety, I think, is that there happens to be actually several values where
Right.
The secant line in this case, so we can see that f of -1 is 1, and f of 2 is also 1. So that secant line has a slope of 0. And there's a whole bunch of places in between -1 and 2 where the slope is 0.
Yep.
So it happens to be that there are lots of values where the tangent line has the same slope as the secant line. But the mean value theorem is not what guarantees that. It just happens to be true for this function. And the mean value theorem doesn't apply. And that's the kind of subtlety. So you could say the conclusion statement of the mean value theorem happens to be true on this.
Just flukily.
Yeah.
If that's a word. Okay.
Yeah. Okay.
Thanks, Tom.
All right.
Okay.
So,
all yours.
Okay. Let's see if I can share my screen successfully here. Let's see. Okay. So I'm attempting to share my.
Yep. Got it. Looks good, Tom.
Screen.
Looks
good.
good.
Okay. So this problem that Steve just looked at was, very much intended. It was more of a theoretical problem. Here's a graph of a function. We didn't have a symbolic form for it. But if you as a teacher were wanting to discuss this example in class, I mean, you could project a picture of it, but you might want to go ahead and generate a graph of this piecewise linear function. And so I thought we'd just illustrate that, and then also look at what happens when we try to do something like a derivative on that graph. Okay, so I'm going to go up on my 84 here up to y1 and actually put in a piecewise formula function that I think will match that graph that we were looking at. Okay, so I'm going to go to the math menu, and if I scroll down all the way past number 9 to summation, log base, there we go. B is piecewise, that's what I want. So let's enter that. And it happens to be, I think the default is 3 pieces. And that's exactly what we want for this function. There's 3 straight line segments making up that. So let's go ahead and say okay for that. And you can see it gives me this nice little template for those 3 pieces. Now I did have to do some analysis, look at that graph and say, okay, what formula would fit over each interval? So I think what I came up with is between -4 and 0, negative x would have been fit that graph. So let's see, it was negative, the domain, the part of the domain that held for was -4, and then it wasn't inclusive. Let's see, we need an inequality here. So I'm going to go to the test menu. That's the second shift of math, and go to conditions. There we go. And so I think I want number 8. So I'm going to go down to number 8. And notice says, okay, put in -4 is less than x, and x is less than or equal. It's ready for me to put in the second value, or the other endpoint of the interval for which that's good. Okay, so that takes care of that first piece. And now for the second piece, I think that's just equal to 0. It's constant. And that's going to be true between 0 and 2, not including either.
Correct.
Let's see, I think that's going to be number 6 is going to be a good match for that.
Tom, one quick question while you're doing this. Maybe Curtis would know this too. If I accidentally made a mistake when I was typing in those conditions, I mean, there's a subtle one here. I mean, what if I said in that second condition 0 less than or equal to x? Does the calculator report any sort of error there when you hit enter?
No.
Okay, so what if I had, instead of 0, I had a -1 in there?
So we had some contradictory.
So we had some contradictory rules. Does the calculator?
Here, 0 works both ways.
Right.
Right. But I understand what you're saying. Yeah.
Does it report it? Does it check that at all, Curtis?
It will. I can't remember off the top of my head. You'll have to try it.
Okay.
I know it doesn't do an error. One of them takes priority. I just can't remember which one.
Oh, maybe it's the first one that it
The first one it encounters, yeah.
Yeah, I think it works from left to right. And so whichever is the first one that it encounters, that's going to be sort of the one that it works
so once it comes up with a value,
then,
it goes on to the next pixel and says, okay,
right.
Yeah, okay,
right.
gotcha.
And so whatever, if there's an overlap, say, between the first piece you defined and the second piece you defined, the first piece you defined is going to win out.
I see.
I think that's how it works. I'd have to try it though. So I'll let Tom finish and I'll play with it and give you a good answer.
Right. So on this one was the one that took, I think, the most time to kind of think through, but I think the formula for this piece ends up being 3x over 2. And then I think I have to subtract 2 to make it line up okay. And so my the relevant interval here is going to be 2. And now I'll go back to that test conditions. 2 less than or equal to x and x less than or equal to 4. So I think number 5 is the appropriate one here. And there we go. I think I've got all the pieces.
Okay.
So let's go ahead and graph it and see what happens. So I'll try just a zoom decimal window to start with. See if that'll work out okay.
Hey, that looks cool.
Oh, looks very good. Yeah, and there's just enough room. My zoom window goes up to positive on the y direction. My y max is 4.2 or something. Just enough to fit the graph there. So very good. Yeah, and if we trace, let's see. For example, let's go ahead and trace over to 2. See, all these values are y equals 0. There's 1.8, 1.9, still 0. When I hit 2, jumps up to 1. There we go. All right.
So, Tom, I know we talked about this, I think, last time, but you'll notice that the calculator did not attempt to connect the graph between, at x equal 2.
Right, and it wouldn't in this window anyway, because even if we had the, I think you're thinking about the detect asymptote.
Yeah.
It wouldn't happen here because with the zoom decimal window, that's happening right at a integer value. So
gotcha.
It's very nice that way. Yeah. Now, what I'm curious about is if I went over to, for example, 2, okay, what would it say the derivative is there? So somebody might look at that and say, well, at 2, I should just use the slope from the right-hand side.
Yeah.
But it's not true because, in fact, our difference quotient, we'd be getting very different values from the left and right.
Yep.
So I'm just curious. Let's see if we go to our calculate menu. Oh, we could try to calculate the derivative there. So let's go down to number 6, calculate the derivative. I'm just curious what the calculator will do, because remember on the 84, it's not able to calculate a true symbolic derivative. What it's really doing is it's calculating a difference quotient that has a very small increment in there. Okay, so let's just see what happens when we try to evaluate. Oh, really interesting. Look at that. Says the slope is 50,000.
How did that happen, Tom?
Well, I'll tell you what it did was it took a value very close to 2 on the right side, evaluated the y value there. Well, you can look at this and say, what would it get? It would get something close to 1.
Right.
And then it took a value just a little bit to the left of 2, an x value, and plugged that into the function. It got 0. So it took something close to 1, something close to 0, something that is 0, and then it's dividing by a really tiny number. So it's getting this huge positive slope.
Gotcha.
And so this is just showing, that it really is doing a numerical approximation. And if you try that where there's a sharp corner, or this is even worse, there's an actual break in the graph, we wouldn't expect it to do a very good job.
Could you try it at 0 too, Tom?
Sure, yeah. In fact, I'm going to go over to, excuse me, let me turn that trace back on. Let me go just, somewhere like at 3.
Okay.
Let's do the slope here. Okay, so I'll do a calculate. Let's go down to number 6. Calculate the slope there. 1.5. That's
Perfect.
right on the money. Okay, and that's because there's no problem. This is a place where the function's differentiable, and it's actually still doing a difference quotient with a very small value, but it's getting a very accurate value. In fact, with it being linear, it's exactly right. Okay. Now you said what would happen if we traced over to 0?
Yeah.
Okay, so let me just jump over there. I'll just type in 0. It jumps right there, and that's where that sharp corner is.
Yep.
Let's go ahead and do a calculated derivative. And keep again, this is not a true derivative. It's a difference quotient. So we should expect maybe something weird to happen here.
Yeah.
With the sharp corner. So let's see. So let's do it. Sure enough,
Boy.
we're getting, and here it's taken a value just a little bit to the left.
Yeah.
A little bit to the right of 0 and done a difference quotient. But because of that sharp corner, we're getting a value that this is not really the derivative, it's an approximation, and we did it at a point where the function wasn't differentiable at all, and so we can't expect that to match up with anything reasonable. And we could jump over to 4 or -4.
Wanda asked really quick, Tom. Wanda asked if the 84 was doing a symmetric derivative, and I think we've talked about that in the past. That's what we believe. TI, of course, is not going to share directly any of their algorithms, I don't think, but yeah, I believe it's doing some sort of a symmetric derivative there.
Or
to answer Steve's question,
is probably the better term, I think.
Yeah.
To answer Steve's question about the boundary values in the piecewise function and what takes priority, so it really does evaluate from left to right, and so whichever
interval it encounters first.
Interval comes first.
Yep.
It's gonna take that. Now, what's interesting, I was just playing with it myself, and even if you define, say you kind of do it upside down and do the right hand side of a piecewise function in the top part of your piecewise function, and then maybe do the left boundaries in the bottom part of your piecewise function, just because it, just to be backwards. Even there, it will work with whatever values are evaluated left to right first. And so it's always going to give priority to the left-hand boundaries.
So let me ask you a question then, Curtis. Tom, would you be kind enough just to put up that graphs, hit the Y equal key?
Yeah.
Sure.
So I would never ask my students to do this, but then you could actually sneakily write those conditions a little bit easier. For example, if you went to the very first condition, let's just say this function were defined for x less than 0.
Yeah.
I could put x less than or equal to 0, and then in the next one, could I just put x less than 2?
Yeah.
So even though it's wrong to write that mathematically with a piece of paper and a pencil, the calculator would evaluate that correctly.
I think so, yeah. As if what you meant was at 0, I'm going to evaluate the second piece of the function at the value x equals 0. The second piece of the function would take over.
Okay. And one more question then, Curtis. Am I remembering this wrong? Is it possible to write that interval that Tom has the blinking cursor on can we just write that as -4 less than x less than or equal to 0?
Yeah. Mm-hmm.
Yeah.
Okay. I mean,
Yeah.
those conditions that you pull off the math menu are very handy. There's no question. But you can also write that in a way that you would on a piece of paper with a piece of paper and a
Sure.
pencil
Mm-hmm.
too, right?
Yep.
Okay. Okay.
Yep. You just wouldn't need the Boolean operator there. Yeah. But
Okay,
if you,
gotcha.
yeah.
So
Mm-hmm.
you're talking like
Oh,
that.
yeah,
Yeah.
that's it, Tom. Yeah, that's it.
And
Yeah, it should be just fine to do it that way. Let's go ahead and graph it
that'll
again.
work just fine.
Graph
Mhm.
just fine. Yeah.
Okay.
In fact, I often do it that way because it more matches
Yes.
what we see in the textbook, and so it works well. Even though it ends up being a little bit longer in terms of keystrokes. And by the
Yes.
way, Steve, I would add that as a caveat that you're pointing out if the main thing you're interested in is having a correct graph that
Yes.
matches this function, you could take some kind of shortcuts and how
Some
you
liberty.
get it. But I would tend to, as a teacher, probably would opt away from that.
Oh, yeah, I agree.
Showing students that I want the stuff to be as accurate as possible.
Sure.
In terms of matching up with right language and stuff. Yeah.
Yeah, that seems like a little bit of a calculator hack,
Well, I would only do that if that was going to be hidden from view. that we didn't have to look under the hood. How did I get my graph? But here I wouldn't mind showing students, look, this is how that function would look if we actually defined it. So
Sure.
all right. I think I'll stop the share and turn it back over to you.
Okay. All right. Sounds good. All right. Let's take a look at problem number 2. Tom, I really like this one. And Curtis, I think you mentioned that Wanda is on tonight. She will remember this, I think. I believe that these two functions in a problem like this was on one of the very first AP Calculus exams in which technology was used or allowed. And students were asked to find the points of intersection of these two functions, or these two graphs, excuse me. I'm pretty sure. Wanda, back me up on that one if you can, will you? So here we go. We have these two functions, f and g. F is x squared, and g, the function g is defined to be 2 to the x, and we know that they intersect at the point where x is equal to 2. Well, how do we know that? We want to solve this. X squared is equal to 2 to the x. I'm not hopeful of being able to solve that analytically, but I can see that by kind of what I'll call inspection, that x equal 2 does indeed work. So find another positive value c that also solves that equation. Well, I suppose I can get that by thinking a little bit about that one too, but I used the TI-Nspire and I graphed those two functions. And it's kind of hard to see my x min and x max, but I think I'm between 0 and 5 over here, and between 0 and about 25 y min to y max. And I could see that these two graphs intersect around this point, and I used the built-in function intersect to find that value, and indeed they do intersect at the point P416. And yeah, on further inspection here and looking at that equation, x squared equal 2 to the x, yeah, 4 works, right? 4 squared is 16, and 2 to the 4th is 16. So we've got 2 points here. But now, Tom, or we think that there's a third one here, Curtis. It says, use the intermediate values theorem to explain why there's also a value of c between -1 and 0 that is a solution to that equation, so that f of c equals g of c. Well, this one's a little sneaky here, but we have to use a good problem-solving strategy. So I'm going to define a new function, capital F, which is equal to f minus g. And I'm sorry that I did not write this over here, but here's this function, capital F. And so theoretically, what I want to do is to find a place where f is 0. Well, first of all, is capital F continuous on that interval -1 to 0? Well, it is. How come? Hey, you know what, Curtis? Let's leave that as a question for the participants. It is indeed continuous on the interval, closed interval -1 to 0. Can you give me a straightforward answer as to why that's true? If it is, the intermediate value theorem must apply. Let's take a look at f of -1. Well, f of minus 1 is little f of minus 1 minus g of minus 1. Am I doing this correctly here? Let's see. Minus 1 squared is 1. 2 to the minus 1 is a half, so that's 1/2. F of 0 is 0 minus 2 to the 0, which is 0 minus 1, which is minus 1. So let's see. F of minus 1 is a half. F of 0 is minus 1. 0 is in between those values. So the value at one endpoint is positive. The value at the other endpoint is negative. It's a continuous function. It must cross the x-axis in at least one place. That's kind of a visualization or a graphical conclusion to the intermediate value theorem. So there has to be a value of c in that interval minus 1 to 0. So the capital F of c is 0, and therefore f of c, little f of c equals g of c.
So, Steve, we do have one response in the
Oh,
chat.
good.
It says a polynomial plus an exponential are continuous. I I think indicating that since both functions are continuous on that interval, then their combined function f minus g would also have to be continuous.
Excellent. Yep, excellent. Little subtlety, little going on in the background, but we don't want to lose sight of those. Yep, very good, Curtis. Good job. So
Look,
I'm going to find this value here between minus 1 and 0. I'm going to have to do this numerically or graphically. I did this on the graph screen. A lot of us like to work there. So here's the graph of f and g once again. And what I did is, of course, use the built-in function intersect once again. I believe I had to pick a lower bound and an upper bound and ask the calculator to search in that interval. And I think that third value is minus 0.767. How about that? So there are indeed three places where these functions, where the graphs of these functions intersect. Well, wait a minute, there could be more. So explain why there are only these three values of C. How come there aren't any others? All right, well, let's take a look here.
hey, Steve, we lost your screen there. I don't know.
You did? Oh, is it still, you see it now?
I don't know. I'm seeing it still, Steve.
You got it? Okay.
I'm
Well, I'll tell you
seeing
what.
Tom's screen, I think.
All right, I'll tell you what I'll do. I'll try this, and we'll try it once again here. How about that?
Ah, now we got it.
Is it back? Okay.
Yep,
Very
now we're
good.
back.
All right, why are those the only three values of C? Well, here's a way to do this. For x less than that negative value, minus 0.767, I can see kind of graphically, and I think I can reason out here that x squared is always greater than 2 to the x. So that means that this difference is always positive. If that difference is always positive, there's no place where that difference is negative. I can't apply the intermediate value theorem again. That function capital F is never going to be 0 again. There's no place less than minus 0.767. For x greater than 4, that exponential function is greater than that polynomial, x squared, that power function. We know in calculus that exponential functions grow much faster than power functions. And indeed, for x greater than 4, that exponential function is always greater than x squared. That means this difference is always negative. There's no change in sign. There's no place where that capital F can be equal to 0. So those are the only three values. I don't remember which of those three that students missed way back on that calculus exam. Maybe Wanda, maybe Mark Corrali will remember. That's a nice problem, which makes use of the IVT.
Hey,
Tom,
Steve,
Wanda,
interject a little bit there?
yes, please.
So I'm trying to remember. I think it happened within the last couple of years. It seemed to me there was a situation where we had a couple of graphs on an AP exam, and students were reasoning that the graphs had to cross because one function value was bigger than the other. at one endpoint and the order switched at the other endpoint, and since both functions were continuous, your graphs had to cross somewhere.
Okay.
And that was by IVT.
Yep.
Well, the reasoning's all kind of sound there, but if you look at the IVT, it doesn't refer to two functions. And really, so students had to be, if they were just going to use IVT and like that, they really needed to set up a difference function like you had there. Say, okay,
Like this one.
exactly. And then you could use the IVT on that function that's the difference between the two. Again, it's not, I'm not saying the reasoning wasn't sound. It's just that the IVT, the way it's stated, couldn't be used kind of just out of the blue without kind of setting up, showing how you could come up with a function for which the IVT could be applied to. So again, one of these kind of subtle things. Students who didn't declare IVT but made some other arguments were sometimes able to make that work. But if you used IVT, it really did need to kind of fit the conditions. So, all right.
Okay. Shall I look at 3, Tom?
Sure, go ahead.
Okay. All right, let's take a quick look at 3. All right, so here we have a new function f. It's defined to be 6 times x to the 2/3. So it says, first, find the absolute maximum and absolute minimum value of the function f over that interval. Well, first of all, I want to make sure that there are absolute or global extrema. I didn't write all of this down here, but let's just think a little bit about this. The very first thing I did was graph this function. And I've got a graph over here on the left-hand side of my screen, again, produced with the TI-Nspire. I've kind of got some solid dots in there at the endpoints of x equal -1 and x equal to 8. It turns out that this function is indeed continuous on that closed interval, -1 to 8. And so, therefore, there must be an absolute max and there must be an absolute minimum. Well, where do we look? I mean, I can kind of tell by looking at that graph, but let's think a little bit about this analytically. Where do I look for those absolute max and min? Well, I look at the endpoints. And I also look at places where the derivative is 0 or does not exist. So, are there any places where the derivative is 0? Well, let's see. Here's f prime. I have a non-zero constant up there in the numerator. There's no way for me to make that 0. In fact, I can see here quickly by looking at that expression that that is undefined when x is equal to 0. This is kind of interesting. X equals 0 is in the domain of the function, but it's not in the domain of the derivative. So let me see if I can summarize this. Are there any places where the derivative is 0? No, there are none. Are there any places where the derivative does not exist? Yes, there is one, x equals 0. So where do I need to look here? This is that table of values method. I have a continuous function on a closed interval. It must have an absolute max and min. I look at the endpoints. And I look at all the places where the derivative is 0 or does not exist. Now, I created a nice table over here using the TI-Nspire. I did this in a list and spreadsheets page, and I think this is kind of cool. I didn't show you everything that's going on behind the scenes, but what I did is I typed in those input values that I found. -1 and 8 are the endpoints, and 0 is the value of x where the derivative does not exist. And then I can simply have the TI-Nspire evaluate the function automatically at each one of those x values, and there they are. And now all I need to do is to pick out the smallest value, excuse me, and the largest value. There's the absolute minimum. There's the absolute maximum. I think that's kind of a nice mix of technology and symbolic results. That's really cool. I think that's a very cool way to use the TI-Nspire. Let's see, there was a part B, C, and D here. Let's see, find the average rate of change of f over the interval -1 to 8. Well, I can do that. I can find that difference quotient. It's f of 8 minus f of -1 over 8 minus a -1. I think I did this correctly. Don't let me make a mistake here. I think it works out to 24 minus 6 over 9. I think that works out to just be a 2. Does there have to be a value c in the interval -1 to 8 so that f prime of c is equal to 2? If so, can we find that value? Well, let's see here. Wait a minute. Let's see what's going on. Must there be a value of c in the interval -1 to 8 so that f prime of c is equal to 2? If so, find the value. Well, let's see. In order for that to be true by the mean value theorem, the function would have to be differentiable in that open interval -1 to 8, and it is not. We know it isn't because there's that sharp edge or corner at 0. And in fact, we just saw on the previous page that it's not differentiable there. Now, there could be a value of 2 in there, or could be a value of c in there so that that's true. But we're not guaranteed that there is such a value. Good. Must there be a value of c in this interval, 0 to 8, so that f prime of c is equal to 3? If so, let's see if we can find a value. Now, be careful. This is a little bit different interval. Is it continuous? Sorry about that. Is f continuous on the interval, closed interval 0 to 8? Yes. Is it differentiable on the open interval 0 to 8? Be careful, the open interval 0 to 8, yes. So let's see. The difference quotient here is f of 8 minus f of 0. I believe that over 8 minus 0. I believe that works out to be 3. So indeed, there must be a value of c so that f prime of c, which would be 4 divided by the cube root of c. We saw that symbolic derivative of c a couple of pages ago. So that must be equal to 3. Let's see, did I do this correctly here? I took the cube root of c to the right-hand side, divided both sides by 3. I think I cubed everything. So c has got to be equal to 64 divided by 27. Very cool. And I think there was one more clever question here. I like this one. Must there be a value of c between 1 and 8 so that f prime of c is equal to 18 divided by 5? Holy Toledo. If so, find such a value. If not, explain why not. Well, let's see. Now, I didn't do this, but I think the very first thing you might consider here, let's see, did we look at that in the previous page? We did not. One of the things you might consider here is f of 8 minus f of 1 divided by 8 minus 1. I don't think that's going to work out to be 18 divided by 5. So I was thinking here that the mean value theorem might apply. So I need some other problem-solving strategy to get this one. So thinking a little bit out loud about this, I'm going to find the first derivative. I've got that symbolically. It's 4 divided by the cube root of x. And I note that that's continuous on that closed interval 1 to 8. Now, I thought a little bit more about this, and I discovered that the derivative at 1 is 4, and the derivative at 8 is 2. Oh, wait a minute. Wait a minute here. Where's 18 over 5? Let's see. So that means 18 over 5 is 3.6. Well, wait a minute. That's in between 2 and 4. So by the intermediate value theorem, there must be a value of c so that f prime of c is equal to that 18 divided by 5. That's very clever. That's a very different sort of use of the intermediate value theorem. I really like that. Tom, want to try a little technology here?
Sure, Steve. Yeah.
Okay.
This is a little
As
bit of
Tom's
a
firing up the technology there, it was commented that one, 1995 is the year that you were referring to
How
earlier.
about that?
Oh yeah, that was the
And
first
then Tom was talking about 2016 ABBC number 1,
Okay.
part D, which
Okay.
is the water tank in and out problem.
Okay. Yeah.
In
Yeah.
case either of you guys were worried that I was off over here looking those things up, that is not the case.
Yeah.
Getting some help from Wanda and Mark.
Very cool.
There's also some commentary from Stephen Beck about some viral YouTube videos about finding the negative solution to that problem you were talking about rather than advanced analytical techniques. There's some other things floating around out there. I'll let others go and find those.
Okay. All right, Tom, maybe one more, maybe time for just one more technology tip here.
Yeah, sure, Steve. Yeah, let me
Okay.
give that a shot. And let's see, I think if I can share my 84 again.
Okay.
All right. All right. So I did want to show something I just thought about recently around this mean value theorem. By the way, folks, we saw a lot of TLAs today. That's a 3-letter acronym. EVT, IVT, even DNE was a 3-letter acronym.
Yeah, there you go.
All right. I'm going to go to my Y equals menu here. And I've put in some things that might look a little startling at first, but just let me explain what's going on here. Down on Y3, I've got a function.
Okay.
And my Y1 and Y2, what I've set up is a general form for a secant line equation.
Okay.
And a general form for a tangent line equation. So my secant line equation, this is what the secant line equation would look like on the interval from A to B.
Got it.
See, and where Y3 is my function. So I've got Y3 of B minus Y3 of A over B minus A. That's the slope of the secant line times X minus A plus Y3 of A. That makes sure it goes through that point A comma F of A, Y3 of A. So there's my secant line. And then Y2 is a tangent line equation through the point X equals C, Y3 is C. So you can see there's the slope of Y3 at X equals C times X minus C plus Y3 of C. Now, you might wonder why I did this. Well, this now really lends itself to that transformation app. If I go to my apps now, scroll all the way down to 0, transform app. And I get the title screen there. And if I go back to Y equals, you'll notice there's a little bit different indicator by Y1 and Y2. These are set up. We basically have what I think of as kind of like sliders for A, B, and C. So let's take a look at what this looks like if I graph it. Okay, so the black graph is my Y3. That happened to be just X squared minus 2. I put in a function. I could change the function. A and B happen to be minus 1 and 2. And notice what I've got is a graph of the secant line that goes through over that interval from minus 1 to 2. And I've got a tangent line at C equals negative 2. Well, if I change A or B, notice that my secant line changes on the fly. And I can also change C. So if I go over to C and increment it, my tangent line is changing. So this gives you a way to try to visualize, okay, where does the tangent line, where is it parallel or have the same slope as my secant line? It looks like this is jumping from integer value to integer value. So it looks like I missed.
Tom, type in 0.5 for C.
Okay, let's give that a shot. 0.5. Oh, nice job, Curtis. Wonderful. Let's look at least eyeballing it looks really good, but we could verify it by actually calculating the slopes of those two lines. But I think this is a pretty neat way to
Yeah.
kind of play with the mean value theorem. And once you go through the work of setting up that y1 and y2, you can change y to 3 to be any function, including ones where the mean value theorem might not apply, and you get some really good graphical evidence of why that's the case. So I think it's just a kind of a neat use of the transform app, and just wanted to show that off. And we're probably about out of time, so I'll stop the share and turn it back over to you, Steve.
Very good.
All right. Well, this was great, guys. Thank you so much for taking the time to put this together and to present that tonight. Appreciate that. If you guys, teachers, are looking for professional development hours and credit, you can certainly email me. I'll put my email down here in the chat. And you can send me a quick email. I'll make sure you have a link for professional development certificate. And then secondly, we will be having our last Monday night calculus of the fall here on December the 15th, I believe, is the next session that we're going to have. So a little bit of time between now and December 15th. We will be doing a pre-calculus live next week. So I look forward to seeing you guys there. But then we're going to take a little bit of a Thanksgiving holiday, and we'll put another one of these on here on December the 15th. So hopefully you guys get a chance to log back in for that. Be watching for communications from Texas Instruments, as well as folks in the AP Calculus Facebook page. We've been able to post some things there. And the topic, as Wanda has so greatly asked, is going to be rectilinear motion. So we'll be looking at motion on a horizontal line, and we'll be checking some things out there. So have a great month here and Thanksgiving, and we'll see you guys here in about 5.5 weeks.
Very good.
Let's see. I think we're finished.